Good morning, guys. Hopefully everyone's having a good day. If you can go ahead and give me a green check in chat, and we'll make sure everyone's with us. I know I only assigned a couple questions last day, just the first page of the learning guide, but if you had anything you wanted clarified on that, you go ahead and put the question into the chat, but I have a feeling there won't be a ton of questions. What I'd like to do today is I want to go through section 2, and then I would like to maybe answer questions if you guys had any on the Unit 4 stuff. I know some of you have written the test and the marks have been pretty good so far. Not pretty good, really good. And I've been getting a few learning guides each day. It'd be great if we could get this test out of the way because we're kind of running out of time. So if you're constantly being behind, you got to get caught up. Got that provincial exam coming in January, and I want to make sure you guys have everything out of the way before we get there. So nobody has any questions from yesterday. We'll just jump right into the lesson here. You recall yesterday we were talking about graphing. We talked about labeling our axes. Units become really important when we're dealing with the questions, especially in graphing. So we're going to just talk a little bit further about it. The idea for today is relations, as well as the ideas of domain and range. So I'm not sure how much we're going to get through today because this is a bit of a longer lesson, but I'll just get through as much as I can. If you guys have any questions, you should feel free to ask. So the first thing we need to do is define what a set is, and then an element and a relation. And it's likely that you guys haven't encountered these terms before, or you haven't encountered them in terms of a math setting. So a set is, this is our fancy math definition, a collection of distinct objects. So a collection of things is a set. In sort of everyday life, you had a set of, I don't know, what do people collect these days? You have a set of action figures or, I don't know, stamps. That'd be a set. They're distinct. They're all stamps. They're different. You know, you have different stamps, but they're just all stamps. So they kind of share things in common. I know you guys don't collect stamps or action figures, but I don't know, what do students collect these days? Does anybody collect things anymore? Maybe records. Maybe you collect records or MP3s or video games. I don't know. An element is an object in a set. So one of the things in the set is the object. Sorry, I had chat off. I've turned it on. Mrs. Wood came storming into the studio this morning. She closed down all of my stuff, and now I had to reboot it all. So I have to kind of reset all this stuff. So chat's on. I noticed a few of you were trying to type, but couldn't because chat was off, but it's on now. So an object in a set is an element, and a relation, this is a bit of a longer definition. A relation is a rule, we'll call it, that associates the elements of one set with another set. This is how we can, bring our things together. And we'll look at some examples here. So likely all sort of new words that you've probably never heard before. But generally speaking, when we first get into the relation stuff, it's pretty straightforward. There's not, in fact, I don't even think we do any calculations today at all. Maybe one or two. But yeah, it's just pretty basic stuff for now, which is kind of nice. Nice little break. So we have an example here we're going to go through. Consider the set of fruits and the set of colors. So we're going to look at fruits and colors. We can associate fruits with their colors. For example, apples may have the color red. Apples can also be green, shades of red, pink, I don't know. They could be lots of different colors, but they may be red. So we can represent relations in different ways, and I think we look at 3 different ways. The first way we're going to represent a relation. Remember, a relation is a rule that associates the elements of one set with another. So in this case, our relation is may have the color. Apple is the first set, color is the second set. So we have 2 sets. How would you represent negative numbers on a graph? That's a really great question, Alex. We will start doing that in Unit 6 or 7. We'll plot some graphs with negative numbers. So right now, all of our graphs have been kind of using this section up here. It's called a quadrant. So this is where we start all of our graphs. If we go down, these values become negative. If we go to the left, these values become negative. So we'll start with negative values on graphs in the next unit or the following one. So the first way we can represent a relation is a table. And here is our table on the right. We have fruits and colors. Not saying that they have to be this color, but you get the general idea. Apples may be red, apples may be green, blueberries may be blue, cherries may be red, huckleberries may be blue. So just kind of going back to our definitions, the heading of each column describes each set. So we have 2 sets in this case. We have fruit and we have colors. And those are our 2 sets. And then may have the color is kind of the thing that relates these 2. So that's the first way we can represent a relation. We can use a nice table like this, and that's it. Just associating the fruit with the color. So that's one way to do it. The second way to do it is a set of ordered pairs. Did you guys do ordered pairs in grade 9 when you're plotting points? Kind of like, you think of like battleships where you had like 2, 3, and then you had to find 2, 3 on a graph. Did you guys do stuff like that in grade 9? Maybe? Yes. Taylor recalls doing stuff like that. Ava as well. Belle. Perfect. So you definitely have seen it in grade 9. So those are ordered pairs. Usually we talk about the first one representing X and the second one representing Y. But perfect, Taylor, X, Y graph. But in this example we're dealing with today, we're not going to deal with X's and Y's. We're dealing with 2 sets of things. Generally speaking, we'll deal with numbers, but to kind of ease into it, we'll deal with objects to begin with. So our set involves fruit and then its possible color. So rewriting everything in the table up above, we're just bringing all this stuff down. Apples may be red, apples may be green, blueberries may be blue, cherries may be red, huckleberries may be blue. So the first thing is the first object, the second in the column is the second object. And we've just rewritten everything along the way. So the kind of mathematical way we indicate a set is we use these squiggly brackets, and we'll just call them braces for now. So these are braces, and the braces show a set. I put in domain and range, but I don't want to talk about it yet. So we're just gonna kind of skip the domain and range for now, all this stuff. We haven't identified what those are. I hesitated as to where I wanted to put it, and then I forgot to erase those. So to show that the list of elements is a set, we put them inside braces. And I will admit that I, for whatever reason, not very skilled at drawing these nice braces. There we go. So that's our braces. We put the elements inside. And Alex, you're quite good. So we can do that. There we go. Does anybody have any questions or anything, concerns, comments? Don't get it? Pretty basic to start. All right, so those are the first two ways. We can use a table, and then we can use ordered pairs. So those are two methods. We'll go to our third method here on the top of the next page, and we can use what we call an arrow diagram. I think that the course calls them something different. I don't know if anybody's watched the videos there from today, but if you have seen it, I wish I knew what they called it. I don't think it's an arrow diagram, but they're the same thing. It's pretty easy to kind of realize what you're dealing with. So the two ovals represent the sets, and we use arrows to associate element of one set with the element of the second set. So if we kind of think back to our table, what was in the first column of our table? What were the fruits? So the fruits that we were dealing with were apple, and then we had blueberries, we had cherry, and we had huckleberries. All right, so that was the first set of things. The second set was our colors. What were our colors? We had the color blue. We had the color green. And we had the color red. So we need to kind of connect our two sets with some arrows. We said up above that apples may have the color, and we decided that apples would probably be red, or apples could be green. So we have apples, and it can be red, or they can be green. Two choices. Blueberries, generally speaking, those would always be blue. Cherries would be red, and huckleberries are blue. So those are our two sets. And I guess the relation, you can write it in here, you don't have to, but we decided this would be may have the color. All right, so continuing through the notes, it's really important to kind of think about the arrows, and the arrows are important in this case. So a relation has a direction. So we need to put that in here. From one set to the other. So this is why it's important. It makes sense to say an apple may have the color red, but it doesn't make sense to say red may have the color apple. So the direction of our arrows is kind of important. So we don't want to draw an arrow from our color back to our objects, just because that would not make sense. So there are other ways to represent relations. Can anyone think of another way to represent a relation? So far we've had, we did a table, we did ordered pairs, we have an arrow diagram. What are some other ways that we could represent a relation? Any ideas? Anything come to mind? What did you guys do a lot with ordered pairs last year? You guys said you'd seen those before. What did you generally speaking do with those? A Venn diagram, a graph, by writing out words. Let's go with all those. I like Venn diagram. We could definitely use that. Alex has said by writing an apple is red. Sure. So words. There's nothing wrong with some words. Avery, graph. That's a great way. Anything else? Venn diagram, Bell's got graph. One other way that we could do it would be an equation. So those are all really good ways to represent relations. There you go. So it's kind of just the basics of this stuff. The definition, sets, relation, what is it, how we can draw them or write them. We're going to start with kind of basic things and then we'll move on next day to functions, which gets a little bit more complex, but this stuff, generally speaking, isn't terribly hard. So let's look at an example. Northern communities can be associated with the territories they are in. So we're talking about cities that are in the Northern Territories. So we've represented it here with a table, and we need to do a few things. We've got a table, but we want to write it in terms of words. And then we're going to do a little bit with these, maybe represented a few other ways. So what is the relation showing? Can we put this into words easily? So the relation shows the association. You know someone from Equilit, Nunavut. I hear it's cold up there. So how are we going to relate these things? What's the relation between the community and the territory? What sort of phrase could I say to kind of relate these two things together? It doesn't have to be complex. Again, into semantics now there, Alex. Let's go with this. A simple way to write the relation between these things is located in. So if I think about the community, I could say Hay River is located in Northwest Territories. I could say Iqaluit is located in Nunavut. So from a set of northern communities, to a set of territories, so for example, the first one that I said, Hay River is located in the Northwest Territories. So this is the relation, is located in. So far we have the relation in a table, we have the relation in words, and we're going to do one more on the next page here. We are going to look at the relation as ordered pairs. This space isn't for anything, so just kind of a formatting error there. So ordered pairs. The communities are the first element in the ordered pair, and the territories are the second elements. So let's write our set as ordered pairs on these lines. So we're going to start our set with these braces, or curvy brackets. That's how we know we're starting a set. Ordered pairs always have two things. So the first one, we said the first thing in our ordered pair is going to be our community. So the first one was Hay River. And that was located in the Northwest Territories. So we're going to go comma, Northwest Territories. We're going to close that bracket, put a comma, and then go to our next ordered pair. The next one represented is Equalit. Make sure I spell this Q-A-L-U-I-T. And Equalit is in Nunavut. Close that bracket. Try to fit one more on this line. The next one is, I'm not even going to attempt to pronounce this. Maybe I should. Nanazivic. We'll go with that. And that is in Nunavut as well. We have Old Crow, which is in the Yukon. Whitehorse. It's in the Yukon as well. And finally, Yellowknife. So at the end of my set, I need to close it with my squiggly bracket. The reason these squiggly brackets are turning out okay is I have to really concentrate when I write them. If I don't concentrate, they just kind of become this mess. So there we go. I have represented my two elements as ordered pairs. So the city and then the territory which it is found in. The last way I can do it is with an arrow diagram. So let's draw some ovals. That's not going to be big enough. One oval. There's my other oval. So in the first oval, I'm going to write all the elements of my first set. So my first set was all the cities. So I had Hay River, I had Equalit, Old Crow, Yellowknife, and Whitehorse. So those were all of my elements of my first set. My second set was all of the territories. So even though some of these cities are in the same territory, I only need to write the territory name once. So if it's the Northwest Territories, I'm just going to put it once. I don't have to write it like 3 times or however many times it's used. So all I have here is Northwest Territories, Yukon, and Nunavut. So I don't need to write them multiple times. Just once is fine. Now I just need to draw arrows to indicate which city is represented in which territory. So Hay River, where was that one? Hay River was found in the Northwest Territories. There we go. And then Equalit is in Nunavut. Nanazivic was in Nunavut as well. Old Crow was in the Yukon. Yellowknife was in the Northwest Territories. And Whitehorse is in the Yukon. Nunavut is spelt wrong. I was just kind of going by what I could see. Suppose I should change it out of respect of the people of Nunavut. I think I forgot a Nunavik, S-I-V-I-K. And that was in Nunavut. My arrow disappeared. There we go. Iqaluit. Yeah, I apologize for my pronunciation of many of these words. Just doing my best here, guys. So again, we have domain and range, but we're just going to pass on that for now. I think it actually comes up in the bottom half of the lesson here. Does anybody have any questions about this? Different ways to represent relations. So we discussed a bunch of different ways: words, ordered pairs, tables, circle diagrams, or arrow diagrams. These are all perfectly valid ways to represent this. So they might ask you to, represent it this way or this way. So you're going to see maybe one of the ways, and they'll ask you to just represent it a different way. That's kind of as tricky as these things get. So we're going to skip the domain and range for now. And we're going to talk a little bit about functions. So we've talked about relations, and now we're going to talk about functions. And on the outside, they're very similar, but they kind of have sort of unique characteristics to them. So a function is a special type of relation where each element in the first set is associated with exactly one element in the second set. So functions are relations, but relations aren't functions. It's kind of like a square is a rectangle, but a rectangle isn't a square. If you ever thought of that. So when we talk about the set of first elements, it's called the domain. And the set of second elements is called the range. So we have domain and range. Now you've seen these words pop up now and again. So we're going to talk a little bit about them. So square is a rectangle, but a rectangle is not a square. Yeah, that's true. If you think of the definition of a rectangle, why is a square a rectangle? Because a rectangle has straight sides, 90-degree angles in its corners, and that's what 4 sides, 90-degree angles. That's the definition of a rectangle. But when you define a square, the sides all have to be the same length. So if I take a square, it's a rectangle. It fits all of the criteria for rectangle, but it does not fit the criteria going backwards. So a rectangle isn't a square because the sides aren't all the same length. There you go. There's your math fact for the day. All right, so here are 2 different ways to relate vehicles, the number of wheels each has. And these are relations right now we're talking about. So let's see if we can figure a relation, function, see what we can do from here. So the number of wheels on A, this is a relation. So a unicycle has 1 wheel, tricycle has 3, motorcycle has 2, car has 4, bicycle has 2. There we go. Same thing over here, except we're going backwards. This relation associates a vehicle with the number of wheels it has. So we're going kind of the opposite way. Bicycle has 2, car has 4, motorcycle has 2, tricycle has 3, unicycle is 1. There we go. So let's kind of talk about what we're dealing with here. So this diagram does not represent a function. Because, so why is this not a function? We defined a function as up above as something that has one item in the first set corresponds to exactly one item in the second set. So which one of the things in the sets is kind of ruining our definition? First set corresponds to one thing in the second set. Where are we running into a problem here? So which one of these items is giving us a relation instead of a function? So Alex is coming up with 2, and 2 ruined it all. This is very true. Let's not take it out on 2. It didn't know what it was doing. So if we go with a fancy definition, there is an item in the first set, in this case 2, that is associated with 2 elements in the second set. So 2 corresponded to both a bicycle and a motorcycle. I'll get to the learning guide in a second there, Alex. Let's just focus on this. The second half of our chart here, the second relation we're dealing with, is that a function or not? Does it represent a function? Does each thing in the first set correspond to something in the second set? Or is there something in the first set that corresponds with 2 things in the second set? This is a bit of a tricky question. Any ideas? Yes or no? What do we think? Nobody feverishly typing. I think I'll just let the cat out of the bag. So the diagram represents a function. Jade went with yes. Jade, you're right. So this is kind of the definition of it. Each item in the first set is associated with one element in the second set. So I guess the catch here is that even though bicycle and motorcycle are both referring to the same number, that's okay. But when we go the other way, the 2 represents 2 things in the second set, it's not a function. So even though bicycle and motorcycle are both representing a 2, the unique thing is that in the first diagram here, the 2 had 2 arrows leaving it. But in the second diagram, each object in my set, each element, only has 1 arrow leaving it. Tricky, hey? So that's the difference between a relation and a function. The 2 has 2 arrows leaving it, but in the second example, the second column of our table, there's only 1 arrow. So to answer your question, Alex, what if there's no arrows leaving it? A function has to have exactly 1 element in the second set. So if it has no elements in the second set, we're not dealing with a function. So what axis would each term if we were representing this in a graph? I don't even think we have to do these as a graph. If we did, what would that look like? We'd have, for the second example here, something like transportation on the bottom, and then we'd have wheels on this one, and we'd have 0, 1, 2, 3, and then we'd have like bicycle. And then we'd have a little dot here. And then we'd have, it doesn't represent well as a chart, so we probably wouldn't do it as a graph just because it kind of looks a bit weird. It might be a good bar graph or something, but generally speaking in Math 10, we're not going to deal with bar graphs. It'll be almost all point plots. So we need to represent it a different way, represent it as a set of ordered pairs. So as a set of ordered pairs, sets always start with squiggly brackets, and then my first ordered pair is going to be 1, and that represented a unicycle. And then I had 2, which was a bicycle, and 2 also represented a motorcycle. And then I had 3 for tricycle, and finally 4 for a car. And then I'm going to close my squiggly bracket. And away we go. We're going to do the same thing with the second one. So see if you can rewrite the second set as a set of ordered pairs. And Avery, so we won't have to look at a graph and tell if it's a function. We definitely will, but there's a really easy way to tell if a graph is a function, and we'll look at that. So let's write the set of ordered pairs for the second one. You guys are well on your way, but I'm going to write it now. If it's a set, I have my squiggly bracket. I don't like that one. Try again. So I had bicycle was 2. Car was 4. Motorcycle 2. Tricycle 3. And unicycle 1. And I'll close my squiggly bracket. Did I go bicycle, 2, motorcycle, unicycle? All right. The last little thing we need to do here, yeah, it's just backwards, just flipping the order of everything. Kind of just further talking about our definitions of these things. So the set of ordered pairs does not represent a function because two ordered pairs have the same first element. Now see if you can figure out the definition for the second one there. So the second column here, the set of ordered pairs represents a function because, let's go with the ordered pairs have different first elements. So just kind of drawing a distinction between relations and functions, just looking at kind of maybe a simple example to get things started here, and we'll look at more complex or complicated examples. But the idea is this: if the number in your first set goes to two different places, it's not a function. If the numbers in your first set, your first column, your first part of your ordered pair, remember we can represent these things many different ways, so it gets a little tricky. If it represents a function, then you're only going to one thing. The last sort of thing that I've been brushing off until now, because I didn't really talk about it, was the domain and the range. All right, so the domain and range are going to be, it's really a straightforward idea, kind of in theory, but it gets harder. So the domain we defined as being the first set of elements. We just called it the domain. So everything in the first column, everything in the first half of our ordered pair, everything in the first circle, that's the domain. The range is everything in the second column, the second half of our ordered pair, the second circle. So if I asked you to write the set for the domain and range for the first table here, first part of the table, we would go something like this. Domain, and it's a set of numbers, so we have our squiggly bracket. And what were all the things in our first bubble, or our first column, or our first half of our ordered pair? What were all the values there? So I look back up to the top, and everything in this first oval is my domain. So 1, 2, 3, and 4. Those are in my first oval. So the domain was 1, 2, 3, and 4. And then the range was everything in my second bubble. So in this case, I had a bicycle, I had a unicycle, I had motorcycle, I had a car, and I had a tricycle. So that was my domain, that was my range. You guys are all over it. How about for the second column of this question here that I was dealing with? You guys probably figured this out already, but the domain is going to be the exact opposite now. So everything in the first oval, that was bicycle, unicycle, motorcycle, car, and tricycle. And the range was the second oval, which was just 1, 2, 3, and 4. What's amazing is that the domain and range, when we just look at it in a super basic example like this one, seems so straightforward, but in practice, when you get into these domain and range questions that you're going to encounter, it's like this really difficult concept. So if it helps, refer back to this stuff we're just finished, because it will get trickier. But if you can figure out the sort of basic definitions of domain and range, you'll be doing fine. So at the end of it, excellent. I have another example here, but I guess I broke it up into a different section. So that's a really great sort of place to end this for the day. I want to just take a quick look at the learning guide. A few of you had some questions on the learning guide. I saw one that just came up. What's the difference between a linear and nonlinear graph? And there was one at the very beginning of class. I'll scroll back up in a second. On the learning guide, page 2, relations and functions. So different ways to represent relations. We talked about 4 different ones, so you can just put them in there, give an example. It's pretty straightforward. In what quadrant of the coordinate plane would each of the following ordered pairs go? Now, you guys mentioned you'd seen ordered pairs. Had you dealt with negative values in terms of ordered pairs or not? You want to just throw it in chat. No, Mr. Borden, have not seen negative values for my ordered pairs. Yes, you have seen. This could get confusing. Alex hasn't. Taylor has. Ava has. Jade has. I think if the majority of us have seen it, then it's probably something that was from grade 9, but maybe we just haven't encountered it thus far. I'll give you a quick, I got 5 minutes here, I'll give you a quick rundown, a refresher if you will, because this is I guess a concept you would have covered in grade 9. So when we have our graph here, and graph paper really helps if you have some at home, drawing these graphs, we have our values. So right at the middle, we call this the origin, and this is 0, 0. And then everything going to the right along here, these are our x values. These are all positive values. So this is 1, 2, 3, 4, 5, 6, 7. And if you want to think about it like this, it's just a number line, right? If I have 0 in the middle here, and I go to the left, then I have -1. I have -2. I have -3, -4. So there's our number line with x values. 0's in the middle, everything to the right's positive, everything to the left's negative. Now, what if I took another number line and I drew it this way with an intersection at that 0 point, and I called all of these values my y values. So everything going up is positive 1, 2, 3, 4, 5, and everything going down is negative. The quadrants, that's a tricky one. There's 1, that's 2, that's 3, and that's 4. Why do we use Roman numerals? I don't know. That's what they do though. So that's just a quick rundown of ordered pairs. Remember, ordered pairs always have, the first term is our x, and then the second term is our y. It's always an x-y ordered pair. There's no exceptions to that rule. All right, so if I need to do some more work on that next day, I'd be happy to do that, but I have a feeling most of you have probably seen it before. Linear means line, and nonlinear means non-line. Kind of a silly way of talking about it. So a linear graph would be something like, I'll use a ruler, make sure I get the line as straight as possible. There we go. So there's a line. Nonlinear would be something like that. So it's not a straight line. It has a curve to it. So if it has a curve, it's not linear. Which is kind of weird because it is a line, but it's not a straight line. So those are the first things. Below are some features of linear, non-linear. We haven't dealt with linear, non-linear, but you should be able to do number 5. It's not terribly difficult. See what you can do. If you need to write a table of values and go from there, and try that. That might help. Ordered pairs, graphs. We will be up to this point here, so this is lesson 2. So just above graphs, we haven't done the vertical line test yet. And we haven't done some of the tricky domain and range ones yet. So we're going to finish up this section next day. what was I going to say? The 3Alex is the X. Always the first one's the X. In the course, I had some extra sheets that I wanted to put up there, but I don't remember if I did. I think in the Unit 5 Lessons Part 1, they might be attached there. Let's just have a look. So we've done the first two. We're good. So we have relations of function, why or why not. So this stuff, we'll run in through this next day. It's pretty straightforward. And domain and range stuff, we'll look at that a little bit more in depth next day. So not a ton of stuff for you guys to do for the weekend here, but you should be up to the end of, almost the end of page 3, just up to the graph stuff. So another few 5, 6 questions. I apologize for not having any time to go through any Unit 4 stuff, but I have a feeling you guys are, for the most part, doing okay with it. I'm going to leave you there, and I'm not sure if I'll be at curling tomorrow or not. I'd really love to come, but I've been pretty busy lately. So hopefully you guys come out to curling tomorrow. I know Mrs. Wood and Ward are really excited about it, and I never curled before, and we had a staff party for Christmas 2 years ago. We went curling. It is a lot of fun. So if you've never curled before, it's not a difficult physical sport. You just go out and throw some rocks down the ice, and it's really cool. It's fun. There's a lot of skill involved, but even the learning curve is really, really low. So just getting started, pushing a rock down the curling sheet is just super fun. Smashing them things into one another. Lots of loud noises. It's great. And then watching your friends fall on the ice is also kind of fun too. So if you haven't curled before, come out tomorrow. It'll be so much fun. And hopefully you guys can get the Unit 4 test out of the way this weekend. I will be in my office till 3:30 tomorrow. If you submit your learning guide before then, I will send you the password for that. And have a great weekend if I don't see you tomorrow. We'll see you on Monday.